Yes? Okay, good. So last time I introduced the Selmer group, and okay, let me quickly go through this. So this is for an elliptic curve over Q, and the Selmer group was introduced in order to get bounds on the rank of an elliptic curve, and to get some understanding of the rank. So the idea was this: you had this first sequence that came from the long exact sequence of cohomology associated to the multiplication by n map on E. And that embeds this E of Q mod n E of Q into some cohomology group, but the cohomology group was too big, and so it was, infinite, whereas we were hoping in a finite answer for this group. And so the idea was to impose local conditions to try to describe which elements here have a chance of coming from rational points. And those were the ones that, when you map them into these restricted direct products into these local H1s, they come from local points on E. Yeah, so that was the definition of this n-Selmer group. It was a subgroup here, defined as the elements here that map into the image of alpha. And the main point of the lecture last time was that this group was the intersection of two maximal isotropic subspaces in a big infinite dimensional space. Well, at least when n is a prime. Otherwise, I guess it'd be modules instead of subspaces. Okay, and so that's the Selmer group. And there's also another group that's associated to the elliptic curve is the Tate-Shaw-Fravich group, written Shaw, and that's the kernel of this vertical map here. And actually, you could even make these short exact sequences on the two rows short exact if you replace these groups by their n torsion subgroups. That also follows from the long exact sequence. So yeah, so it follows from that. If you just look at that diagram where you replace these groups by the elements of order n in both of them, you can extract from that diagram a short exact sequence like this, where here's the group you're interested in. Here's the group that ordinarily you wouldn't be interested in, except that it maybe tells you something about the group that you are interested in. And then there's the group that, well, you again wouldn't be interested in, except that it's sort of the abstraction to measuring what you can actually compute to what you're interested in. So, okay. And then that turns out to be the n torsion. I mean, that's the kernel of this map on n torsion. Yeah, so this is, okay, so that's, right, so that just follows directly from the definitions. And now what we're going to do, in order to get more information about E of Q, we're going to look at this for various different n's and try to piece together the information for a different integer to n and to say more. Okay, so in particular, what we're going to do is take n to be a prime power, so power of E, so power of p, and then we're going to take the direct limit of each of the sequences as E increases. So okay, so what happens when you do that? Well, you get a new short exact sequence. Now, okay, so what this group here, I can think of also as E of Q tensored with 1 over n z mod z. And if I view it that way and then take these powers of p, so then it's E of Q tensored with 1 over p to the e times z mod z. And if you view it that way and then you take the direct limit, you'll get this. Because qp mod zp is the same as the direct limit of 1 over p to the e z mod z. Okay, so that's what you get there. And what's the direct limit of the Selmer group? Well, that's not really anything particular, so you just invent a new notation for it. So the new notation for that is it's called the p to the infinity Selmer group. Okay, so that's just by definition the direct limit of those. And then what's the direct limit of these? Well, these are just, here we're just taking the p to the e torsion of the Tate-Shaw-Fravich group for larger and larger e. And the direct limit is just with respect to the inclusion maps. And so it just takes the union of the p to the e torsion for all e. And so that's called, well, it's all the elements of p power order. And so often people write like this. It's the p to the infinity torsion. So that just means that it's all the elements of p power order. Okay, so you get this short exact sequence. that's associated to the elliptic curve E, well, and the prime P. Okay, so let's give this thing a name. Let's call it, let's see, oh, I can use, what's this? Am I allowed to write with this? Let's call it the sequence associated to E. Is that visible? Oh, it doesn't look like it's a different color though. Okay. Anyway, so let's just call this whole sequence will be just the sequence associated to the elliptic curve E. All right, and what are the groups in this short exact sequence look like? Well, first of all, they're all torsion abelian groups. Every element is of p power order, and so you can think of them as ZP modules because of that. And so yeah, so in fact, each term in this sequence is a ZP module, where ZP is p-adic integers, and it's of the form. Well, I mean, each one is what's called a module of cofinite type, which means, well, its Pontryagin dual is finitely generated. And more concretely, it looks like a power of QP mod ZP, so where S is some non-negative integer, and then plus direct sum with some finite abelian P group. Okay, so yeah, and in fact, some of them are even simpler than that. I mean, this first one, well, because it's tensored with QP mod ZP, anything that's finite, and if there's any torsion in E of Q, it'll disappear when you tensor with this group. And so the first one is really just a power of QP mod ZP. In fact, it's QP mod ZP raised to the rank of the elliptic curve. So if you knew what this sequence was, it would directly tell you what the rank of the elliptic curve is, which is nice, because that's sort of one of the main goals. Whereas, I mean, back here, I mean, even if you knew exactly what this group was, you wouldn't quite know what the rank was, because this could have a contribution from the torsion subgroup as well. So okay, so this actually is more information here, because this, well, if you could figure out what these terms are, and yeah, and so what the claim here, yeah, so the middle one is really just of this type, and yeah, I mean, it's a non-trivial theorem that this S is finite. It comes from the finiteness of the Selmer groups and things like this. And then on the right-hand side, what kind of group is that? Well, conjecturally, I mean, if you go back here, that Tate average group is supposed to be a finite group, and now we're taking all the p power, all the elements of p power order in that finite group, so it's going to be even more finite. And so at least so conjecturally, this thing is finite. So all right, so I mean, we don't know for sure it's finite. I mean, it's not a theorem yet. There could be some QP mod ZPs hiding in there, and that's. Sorry, oh, is there a question? No. Okay. Yeah, so there could be some QP mod ZPs hiding in there, and that would mess you up if you suppose you were able to compute Selmer groups, because Selmer groups are the things that tend to be computable. So okay, you compute this. You count how many QP mod ZPs there are in here. You hope that number, which is sometimes called the P co-rank, or the P Selmer rank, or something like that. You hope that that's really the rank of the elliptic curve, but there could be, unless some of it sort of escapes into the Tate-Charpf-Average group. So I mean, that's one of the reasons why people want to know that Tate-Charpf-Average groups are finite. Okay, so okay. Now what are we going to do in the rest of this talk? We're going to try to look at this sequence where E now varies. So for every elliptic curve, you get one of these sequences, and you can look at the isomorphism type of that sequence as just a short exact sequence of ZP modules. And you can ask, how often does each abstract short exact sequence of ZP modules arise? Okay, so, and if you know that, then I'll tell you, for example, how many elliptic curves have rank 2, for example. What's the density of elliptic curves of rank 2? Because you can just read it off from this sequence. If you really know the whole sequence and not just the middle term. Okay, so all right, so so we're going to describe a model that's in some ways generalizes the model I gave last time for the P Selmer group as an intersection of maximum isotropic. And so for this, so we need to, so the ogre returns. So, so last time, we had the ogre of a finite field, but today we're going to have a much bigger ogre. Okay, so what was that defined to be? I mean, this was, just to remind you, this was the set of all possible maximal isotropic subspaces of, well, of the quadratic space consisting of a 2n dimensional FP space with the quadratic form that was just the sum of, was like an inner product kind of thing. So it's it's this quadratic form in the 2n variables. And so yeah, so that was the definition of this. And it was, so far it was just a set. And you can think of this also, if you want to, as a subset of the points of the Grassmannian. So the Grassmannian is a variety that classifies subspaces of a vector. You start with a fixed vector space, and you try to count how many subspaces there are of a given dimension. So if you look at inside FP to the n, and you count look at all the n-dimensional subspaces, well then, this set is going to be a subset of those, because there's this, this is the difference here is that this has the extra condition that the quadratic form needs to vanish on the subspace. Okay, yeah, so this by definition is the set of all n-dimensional subspaces of this V, which is Fp to the 2n. Okay, but now in order to talk about these p to the infinity Selmer groups, it's not going to be enough to just have ogre of Fp. We're going to want to have ogre of Zp, ogre of the p-adic integers. So like a p-adic ogre. And then so in order to, and if I'm going to do that, I might as well work even more generally and just talk about ogre of any commutative ring. So what is that going to be? Well, first let me say what is the Grassmannian? What are the a-valued points of the Grassmannian? So what does it mean to have a? So this would mean you start out with an ambient module that's like a to the m, and then you want to look at all the rank n submodules of that. Except it's not really all rank n submodules. You really should restrict to the locally free ones. So locally free rank n a submodules. So let's call it Z. Z contained in a to the m. And that's not all. You also have to, if you're working over something that's not a field, then you should also insist that Z be a direct summand. It's just what the Grassmannian parameterizes. Yeah, and then this turns, yeah, so then now A is now any commutative ring. So that's any commutative ring. And now, okay, so ogre is going to be a subset of this. So ogre n of A, well, it's going to be a subset of, this when m is taken to be 2n. And so it's the set of submodules in Grassmannian of n rank n things in a 2n rank 2n thing. And the only extra condition is that it already has the right rank. So the only extra condition is that the quadratic form should vanish on this. The quadratic form, that makes sense over any ring. I just evaluate it on a to the 2n. Okay, so that's the definition of the ogre functor. And now the ogre functor is represented by a smooth projective ogre scheme. So just as the Grassmannian is represented by a scheme. So yeah, so these both. So okay, so let me write that. So this this thing. Oh, did I reverse? I probably reversed the n and m. Okay, that's n and m. So this and the ogre n, those are represented by, well, by smooth projective schemes over Z. So that means you can plug in, I mean, if it's over Z, you can plug in any ring. Okay, so smooth projective schemes over spec Z. And the scheme ogre n, it actually has two connected components. As it turns out. So you might be wondering, how can you distinguish the two components? I mean, so there are two kinds. It turns out there are two kinds of maximal isotropic subspaces. So how can you tell which ones belong to which component? And well, that's kind of a tricky question to answer. I mean, because neither component is somehow distinguished by itself. It's only but what you can answer is, I mean, because there's not a canonical choice of one of those. So it's hard to point to one of them. But what you can say is a condition that tells you when two maximal isotropic subspaces belong to the same component. And so here's a fact that is a classical fact that tells you how to distinguish these components. So over any field K, so let's look at points of ogre n over K. So the condition is that two of these, so now we're just talking about subspaces. We're just talking about n-dimensional subspaces of a 2n-dimensional quadratic space over K. And two of these things, say Z and Z prime, two maximal isotropic things, they are in the same component. If and only if, so it all depends on the dimension of their intersection. So if you take the intersection, you take the dimension of that vector space, well, that's going to be something between 0 and n. And the condition is, it depends on the parity. Now, what do you think I'm going to write here? What parity is going to make it so they're in the same component? Yeah, n is a good guess because it might be that Z is equal to Z prime, in which case they should be in the same component, right? So okay, so that's the condition. I mean, it's not obvious that actually defines an equivalence relation, for example, and that there are only two. But I mean, this is a classical thing. That's true. Okay. Anyway, so you have this. So that's sort of how you can distinguish them. And but how are we going to use this? As I said, we're going to look at a p-adic ogre. So we want to know about the ZP points of ogre n. And so in order to study that, we're going to look also at the points of ogre n over Z mod P to the EZ for each E. And we're going to compare those things. And in particular, there's a map from ogre n of Z mod P to the E plus 1 Z. I mean, they form an inverse system. An inverse system of ogres. Okay. Okay, and then so this map, what can you say about that map? So there's a clue that whatever I'm going to say is going to follow from smoothness. And well, first of all, it's surjective. That follows from smoothness. But also, the fibers of this map, they have constant size. I mean, it's almost as if ogre n were just like an affine space of some dimension. And then so this reduction map, it would be like all the fibers would have constant size, and the size is just p raised to the dimension of ogre n. Okay, so and now what that means in terms of choosing things at random, suppose you attached the uniform probability measure to each of these finite sets. So you choose one of these at random, and then the uniform probability measure on this one is compatible with the uniform probability measure here because of this property that it's sort of a finite, it's a fixed number to one map. So you can and from that, so therefore you can get what I'll call a uniform probability measure on the inverse limit. So get a uniform probability measure on, well, on over n of zp, which is the same thing as the inverse limit of these finite sets. So it's kind of like a Haar measure on this. I mean, it's not a group, but it's some profinite set. Okay, so that's nice, because that means now we can choose maximal isotropic ZP submodules at random, and that's what's going to be used in the model for the P to the infinity Selmer group. Okay. All right. So now I'm ready to tell you the model. So this is going to be the linear algebra model. That's the analog of the thing about maximal isotropic FP vector spaces. So except this time, instead of FP to the 2n, start with ZP to the 2n. And I'm also going to fix one maximal isotropic submodule of this. And so I'll take the easy one, which is ZP to the n crosses 0. Okay, so that's a 0. That's a 0 in the other ZP to the n. So okay, so that's like half of V. And that as I showed you last time, that's something that's going to be an example of a maximal isotropic. Yeah, direct summand and so on. Okay, and then I'm going to choose a second one at random. So choose, I mean, I could have, okay, so I should choose a second one at random. So a random Z, which is also it's also a maximal isotropic direct summand in this rank 2n ZP module. I mean, I could have chosen both of them at random, because it turns out that it's still true that the orthogonal group, that the ZP points of the orthogonal group act transitively on the maximal maximal isotropic submodules. So that's why it was okay for me to fix one of them, because I could just, I mean, it's really only the relative position of the two that matter. Okay, so now I have two of these. I have Z and a W, and now from this I can form a short exact sequence. So the first term will be, I intersect the two things. So that'll be some ZP module inside V, and I tensor that with QP mod ZP. Next, instead of intersecting them, I tensor first and then intersect. I mean, this is not the same as the first term, because, well, I mean, the first term is going to be non-zero when Z and W really line up sort of exactly. There's a ZP line or something that's contained in them. Whereas the second intersection will be non-empty even if Z and W sort of agree mod P, and then there'll already be some stuff in there. And the obstruction, okay, so the difference between them is going to be measured by some other group, which I'll just call. Okay, I'll give it a name in a second. But so okay, so this thing here is happening inside this intersection is happening inside V tensor QP mod ZP. All right, so we'll call this one R. So that's R for like rational points or rank or something. This one will be called S for Selmer group. And this one will be called T for a Tate-Shafarevich group. So this is defined to be S mod R. So I just force it to become part of a short exact sequence. Okay, and I mean the reason that they're called that is that they're supposed to model. This is supposed to be a model for the sequence I had way back here. Yeah, so remember this sequence? So this was a sequence that came from an elliptic curve. So from an elliptic curve, you can build one of these sequences. And now the idea is that this linear algebra construction is supposed to provide a random sequence that has the same distribution as these. So, okay, so first of all, well, it's not quite true. Because, I mean, this so far depends on a choice of n. I mean, I fixed this dimension of the ambient space here. And so we're going to need to let n grow. So the first theorem, and this comes, yeah, and this, maybe I should have said, all this, what I'm talking about today is based on an extension of the, well, it's a sequel to the Poonen-Rains paper, and this one, we joined forces with some other people, so, Bhargava, so, it's, okay, Manjul Bhargava, Daniel Kane, Hendrik W. Lenstra Jr., that's me, and Eric Rains. Okay. So the first theorem is that, well, maybe this is not too surprising, but the limit of this distribution, so okay, so this is a distribution on short exact sequences of ZP modules, and the limit of this distribution exists. So if you fix a particular abstract sequence of ZP modules and you ask what's the probability that this gives that sequence, then you get a certain number, then a certain probability for each n, and those numbers converge. And they give you something that's an actual probability, a discrete probability distribution on the set of such abstract short exact sequences. So the first thing is that this limit exists. I mean, the real theorem we would like to prove is that this actually says something about elliptic curves, but that part is only a conjecture. So, yeah, it's by the same people. So, Book Lepper. Okay, so that's the limiting distribution. So this conjecture is that the limit of the distributions of the theorem, the limiting distribution equals the distribution that came from the arithmetic of elliptic curves. So it equals the distribution of the sequence, the thing I called sequence associated to the elliptic curve, as you vary E on among, so all the elliptic curves over Q. That was the notation I introduced last time. Okay, so this is supposed to tell you everything you want to know about the statistics of elliptic curves, as far as ranks and Selmer groups and Tate-Chaffer average groups. So this is one big package that's supposed to tell you everything. So in the rest of the talk, I'm going to explain how this tells you everything and say what it actually predicts. Okay, so let's start with the consequences of this conjecture. What does this tell you about ranks of elliptic curves? Well, I mean, where's the rank? Okay, let's watch this. So compare this with this. This is supposed to. Okay, well maybe I can. Can you see them both? This is supposed to be the model for this. So the rank is supposed to be the number of. I mean, you can measure this by counting how many copies. This is just some power of QP mod ZP. You can just count how many factors there are. So you can do the same thing here, and then that should be the model for the rank. So yeah, so if you take that first thing, the thing that's called R there, is Z intersect W, tensored with QP mod ZP. Well, I mean, just by the way it's formed, when you tensor a finally generated ZP module with QP mod ZP, you're going to get some power of QP mod ZP. So it'll be this raised to some non-negative integer R. And it'll be equal to that, where R is the dimension of the intersection. Well, maybe in order to talk about dimension over vector spaces, I'll tensor them both with QP. So I'll take Z tensored QP, so it is, I guess, over ZP, and intersect that. So that's a QP vector space, and take that and intersect it with the same thing for W. So okay, so that's the prediction for what the rank of elliptic curve looks like. You choose the Z at random, and you look at how the vector space it spans intersects with the standard maximal isotropic W. All right. Now, so what actually happens when you do this in the model? So, well, I mean, if you imagine a big QP vector space and you choose two subspaces of dimension n at random, you wouldn't expect them to intersect. I mean, the expected dimension of two n-dimensional things in a two n-dimensional space is 0. So you would expect that they wouldn't intersect at all. And except for one thing. So here, sometimes, well, a lot of the time you're going to get 0, but there's sometimes it's impossible to get 0. And that's because of this thing about ogre. So back here, half the time when you intersect two maximalized tropic subspaces, you will get something that is odd dimensional. So half the time it's impossible to have a 0-dimensional intersection. And so what actually happens is, well, it tries to be as small as it can. So with probability 1, the intersection will either be 0-dimensional or 1-dimensional, and it's just the minimum that's possible given the parity constraint. So it's going to be this. It's going to be 0 for z in one of the components. If your random z happens to be in one component of this ogre, and it's 1 for z in the other. Yeah, and this squiggle, well, as we learned this morning, the squiggle could mean anything. But in this case, it actually means something precise. Here, I mean outside a lower dimensional locus in ogre. And lower dimensional locus means, I mean, we're talking about a p-adic, this set of p-adic ZP points of ogre. So lower dimensional means it's going to be R measure 0. So this is going to be, so this means that I can, if it's from the point of view of probability, I can just ignore it. So measure 0. And so this means that 50% of the time, this R is going to be 0, and 50% of the time it's going to be 1. And so then if you now accept that, if you now accept the conjecture predicts that this R should be modeling the ranks of elliptic curves. So if you accept this Booklepper conjecture, it'll tell you that, well, that 50% of elliptic curves have rank 0, and 50% of elliptic curves have rank 1. And well, then there are a couple of extra things, but they're 0%. I mean, there are elliptic curves of rank 2 and 3, and maybe even bigger numbers too. But they should be asymptotically negligible. They should be 0%. That's what this thing is predicting. And well, I mean, there are some points in here where R is bigger too. You just happen to get really unlucky and you land on this measure 0 subset. Okay, so all right, so this is 0% have rank greater than or equal to 2. Okay, so that seems to agree with what other people have conjectured. So, I mean, we take this as being, well, some sort of evidence in some sort of weird sense that this model is a good model. So, all right. So, yeah, actually, let me forget. Okay, so let's now look at the next term in the sequence. So, well, maybe I should show you the sequence again. So remember that. So this we were just talking about this part of the random model, but now let's look at what this part says. So this was the part that was supposed to be modeling the p to the infinity Selmer group. So what does this tell you about p to the infinity Selmer groups? And maybe you don't care about p to the infinity Selmer groups. Maybe you really want to know about more concrete things, like just these finite Selmer groups, like the p to the e Selmer group, where e is not infinity, e is the number. So what does this model predict about that? Well, okay, so I'm going to fix the prime p, and so one thing I can say, I mean, well, here this is telling you what the p to the infinity Selmer group looks like. So in order to pass from the p to the infinity Selmer group to the p to the e Selmer group, well, you need to know this fact, that if you take well, at least under a hypothesis, if there's no rational p torsion on the elliptic curve, it turns out that you can recover the p to the e Selmer group of an elliptic curve from the p to the infinity Selmer group, which is this big thing that has copies of qp mod zp in it, by just taking the p to the e torsion in that. I mean, this is some big, humongous torsion abelian group, and you just take the elements of order p to e. And that works whenever there's no rational p torsion. So that's elementary Galois cohomology calculation. Yeah, and also, this is good news because most elliptic curves don't have rational p torsion points. I mean, especially when p is like 11 or more. So then, yeah, well, but even for small p, it's pretty rare. Like, I mean, most elliptic curves do not have two torsion points. Because you write down a random cubic, it's not going to have a rational root. So yeah, and you can prove that by saying, I mean, because the cubic is most of the time, in fact, it's most of the time that the cubic in your Weierstrass equation is going to be irreducible. And that follows from the Hilbert irreducibility theorem. Because it's somehow x cubed plus ax plus b is irreducible over q adjoint ab. And Hilbert irreducibility tells you that it will stay irreducible most of the time if you plug in particular rational numbers for a and b. And the same kind of argument works in general. So the conclusion of that is that this hypothesis is actually true for 100% of E. And 100% is good enough for what we're trying to do. Because this is all probability anyway, so nobody cares about the 0%. Okay, so, all right, so this is true by the Hilbert irreducibility theorem. So, okay, so as for all practical purposes, the P to the E Selmer group is the P to the E torsion in the P to the infinity Selmer group. And that means that we can model the P to the E, that this model actually is predicting something about P to the E Selmer group as well. Because you just take whatever this model gives for the P to the infinity Selmer group, and then that'll tell you what the P to the E Selmer group should be. And so as a corollary, if you accept this conjecture that this really is modeling elliptic curves, then it will tell you that the distribution of this finite abelian group, this P to the E Selmer group, is equal to the limit as n goes to infinity of the same process you do here, except instead of intersecting these things tensor with QP mod ZP, you just take the P to the E Selmer, P to the E torsion in both of them, which amounts to taking the distribution of an intersection Z intersect W, where these Z and W are now their maximal isotropic submodules over Z mod P to the EZ. So I mean, this is just, I mean, if E were 1, this would be exactly what we talked about the last lecture, where you choose two maximal isotropic FP subspaces, and you intersect them. And you look at and that intersection is supposed to model the P Selmer group. And now we're just doing the same thing, except we're taking the Z mod P to the EZ raised to the 2n, and inside there, choose two maximal isotropic submodules, each of which is a direct summand, and intersect those. And this is telling you that intersection should be the P to the E Selmer group. It should be the model for that. In fact, that's how we came upon this thing. We started with this thing, and then we tried to reverse engineer it to try to see what would happen if you put all the P to the E's together. And this is sort of what came out. Okay, so yeah, so let's see, how much time do we have? 10 minutes, is that right? Okay, 10 to 15 minutes. All right, so maybe I can say, I mean, from this you can extract all sorts of other predictions about P to the E Selmer groups. For example, this suggests, maybe it doesn't quite imply but it suggests, for example, that the expected number of, well, you can try to study the average size of the P to the E Selmer group, or you can try to study the moments. You could try to study the average of the square of the size of the P to the E Selmer group. And those questions have ugly answers. And so we don't want to ask those questions, but there's a closely related question that contains the same information that has much nicer answer. So that's if you count, instead of the moments, which would be like counting all, well, okay, let me just write this. So if you look at maps from this to this intersection, which is supposed to be like the Selmer group. Actually, I shouldn't call this conjecture. This is really a theorem. But it's supposed to be, I mean, this is supposed to be model, for these Z and W, this is supposed to be modeling the P to E Selmer group. But what you can prove is that if you look at the maps from this module, Z into here, if I didn't say injective, how many would you get? I mean, this is a Z mod P to the E module. So to describe such a morphism, you just say where each basis element goes. And so the number of elements, the number of homomorphisms would just be the size of this group raised to the M. And so that would be the moment. That would be the mth moment of the size of this thing that's modeling PDE Selmer group. But that turns out to be not a nice question in terms of not getting a nice answer. But if you instead insist that the homomorphisms be injective, so that means you're essentially counting independent you're counting how many M tuples of independent elements you have in this module. Then that turns out to have a nice answer. It turns out to be P to the E. It's just a power of P, just a big power of P. Okay, whatever. And from this, you can, if you start adding up, you can reconstruct the moments from this. But the answers, as I said, are not so nice. Yeah. So for example, if you want the average size of the P Selmer group, well, that's the same as counting all the homomorphisms from Z mod PZ into your thing. And most of those homomorphisms are injective. Z mod PZ mapping into something is going to be injective, or else it's going to be 0. And so there's one of them that's 0, and according to this, there are P of them that are non-zero. So that tells you, this predicts, for example, that the average size of the P Selmer group should be P plus 1. And so you can do this for any P to E. Okay, so the last thing I want to talk about is what this predicts for the last term in this model. Okay, so let's go. Is it okay to remove this? Yes? Okay, so let's go back to this model. So we said that this told us something about the ranks. This told us something about the Selmer groups. So now let's see what the model predicts about this, which is supposed to be the model for Tate-Shafarevich groups, or at least the P primary part, the P to the infinity torsion of the Tate-Shafarevich group. Okay, so the consequences, now we're talking about consequences for SHA, for the Tate-Shafarevich group. All right, so so one thing you can say, by the way, just from group theory, when you do make a construction like this, it always turns out that really actually S contains all the information. It turns out that R is just the maximal divisible subgroup of S. And T always turns out to be finite. So that means as a corollary of that, the conjecture that this sequence actually models elliptic curves, that will tell you that the thing that this T is modeling, which was the P to the infinity Selmer group of elliptic curve, that's going to be finite. Well, not for all elliptic curves, but at least for 100% of them. So for 100% of E's. I mean, these are all probability density things. So you can't say anything about it. I mean, terrible things could happen for a 0% of the elliptic curves, and this model wouldn't know anything about it. This conjecture wouldn't know anything about it. So, but as far as yeah, okay. So, but at least it's predicting what we think should be true, that these groups should be finite. So it's at least compatible with things that people believe. Okay, now, but suppose we want to know more than this. So, I mean, this conjecture is telling us really what the distribution, not only that it's finite, but it's telling, like, how often does each finite group arise? It's just like, it's very much analogous to the Cohen-Lenzer heuristics, where you can ask how often does a particular group arise as a class group. And now we're just asking for arising as a Tate-Shafarevich group. And several people have studied this question, and in fact, well, there are 3 answers. There are 3 predictions. So, and in fact, they're refined in that you can condition on the rank and still make a prediction. In fact, I mean, maybe it's even worth saying that the Tate-Shafarevich group itself, it's almost as if it's a different group for each depending on what the rank of the elliptic curve is. It's almost acts like it's a different kind of group. So these distributions are all, I'm gonna condition on the rank of E. So I'm gonna look first at, for example, at all the rank 1 elliptic curves and see what the distribution of SHA is for those. And we'll, and try to predict all these. So we're gonna condition on the rank, and there are gonna be 3 distributions on the set of possibilities, which are gonna be finite abelian P groups. Well, I mean, some of them shouldn't arise since SHA is supposed to be a square order, but okay. Anyway, so it's and each of these distributions, I'm going to describe 3 distributions, each one of which is conjectured to be the distribution that we're looking for, which is the distribution of this P primary part of SHA. For E varying over elliptic curves of rank R. Okay, I'm back. All right, so here's what you do. So, well, here's the first prediction that was made for what the distribution of Tate-Charpevre groups should be, was made by Christophe Delaunay, and he made a prediction based sort of by an analogy with the Cohen-Leinster heuristics. And so he used the idea that it should be proportional to 1 over the size of the automorphism group, but now this group, the groups that we're talking about for Tate-Charpevre groups, they have extra structure. There's a non-degenerate alternating pairing on the Tate-Charpevre group of an elliptic curve. And so the only groups that should arise are the ones that admit such a pairing. So, and when you look at the relative frequency of those groups, you should think of the whole structure, the group equipped with that non-degenerate alternating pairing. And then the automorphism group should not be just the automorphism group of G, but the automorphism group of the pair, consisting of the group with that non-degenerate alternating pairing. And so, okay, I'm not done with the formula, but so you choose any non-degenerate alternating pairing from G cross G into QP mod ZP. So alternating just means that if you take x comma x, then that pairs to 0. And then that implies that x comma y is minus y comma x. So it implies anti-symmetric. Yeah. So I mean, if this doesn't exist, if you have a group G for which this doesn't exist, which is going to happen when G is not of the form H cross H for another finite group. So if it doesn't have that shape, then the probability should be 0. Then that those groups are not supposed to arise at all. That's part of the prediction. And okay, but when G does have the good form, when G is like H cross H, and then you have this non-degenerate alternating pairing, you can choose any one. They're all basically the same. And you can look at the automorphism group, and the probability that G arises should be proportional to 1 over the size of the automorphism group, weighted by some power of the order of the group. And well, then you have to. And it turns out. I mean, these numbers don't add up to 1, and we've had problems with this. I mean, you don't want probabilities adding up to more than 1. So you have to normalize by putting in a constant here. And the constant, I mean, it's going to look like it. I mean, so it's just a number that depends on r, and we fixed r, so it's this. So, all right. So this is something that doesn't depend on the group. It's just normalizing it so that the probabilities add up to 1. And then, but this is the main thing. So that was his prediction. Okay, and there wasn't any real there. I mean, there wasn't any. There wasn't any arithmetic justification for it. It would just look like what would happen if you took the Cohen-Leinster heuristics and you changed some of the p's to p squared and things like this. All right, so that's one prediction. Now, so that's one conjectural distribution. Let me tell the other two. So the other one is from this paper again. So if here, this is an analogy to the Friedman-Washington construction of the Cohen-Leinster distribution. So what Friedman and Washington did was they chose a random matrix over a random square matrix over ZP with respect to Haar measure of some size. And then they thought of that as a map from ZP to the n to ZP to the n. And then you take the co-kernel of that. And the co-kernel of that gives you, well, with probability 1, you get some finite abelian group. And then that was supposed to look like the class group, the p part of the class group of a quadratic imaginary field. So that was their heuristic, which was motivated by some function field calculations. Now here, we're trying to get a different distribution for the Tate-Charifrege group. And what turned out to work is, well, for rank R elliptic curves, choose a square matrix, but not just any old matrix. It should be one that has something alternating about it. So it should have the property that transposes minus A. So it's called alternating matrix. And also, in order to get the correct rank, the rank of this matrix. This is not rank of elliptic curve. This is rank of a matrix. So, dimension of the row space. So okay. So it's this rank should be 2n. So if you do that, then so then you can write down this map from ZP to the 2n plus r to ZP to the 2n plus r. That's given by this, just the sort of the associated linear transformation given by A. And you can form the co-kernel, just as in Friedman-Washington. But I mean, this is going to be not a finite group. That's bad news if it's supposed to be a Tate-Charifrege group, because this had rank only 2n. I mean, it had rank 2n instead of being full rank. This is going to be a finitely generated ZP module of rank R, but it'll have a torsion submodule, and so you take the torsion subgroup of that, sort of torsion submodule, and then that. Oh wait, I guess not to make an exact sequence. I should write that, but now I take the distribution of the torsion subgroup of that, torsion submodule of that, and you can show that has one of these alternating pairings coming from the fact that A is alternating, and then that's supposed to be the distribution of a Tate-Charifrege group. That's what a Tate-Charifrege group should look like. It should look like the torsion subgroup of a random co-kernel. Okay, that's the second distribution, and there's one last distribution, which is also from this paper, which is the one actually just coming from the model I told you with the RST. So you choose a random maximal isotropic thing. So in over n of ZP, and you form, but now in order to look at rank R elliptic curves, you should condition. Well, it's not really conditioning, but you're restricting where it comes from. You should sample Z from the sub variety in here, where the rank of the intersection, which is supposed to be modeling the rank of the elliptic curve, that should be R. And now, based on that, you form from that Z. You form from the Z and the W. You form this random exact sequence, and then the T was supposed to be the model. So you take the limit. Oh, I forgot to take the limit here. So take limit as n goes to infinity here of this distribution. Okay, so and now you take limit as n goes to infinity of the distribution of T. And then that's supposed to be, again, the distribution of the Tate-Charles group. And so let me end by saying, okay, this might look like bad news because there are too many conjectures for all the same thing. There are too many competing conjectures. But the good news is what we prove in this paper. One of the main theorems is that for each value of the rank, so for each value of the rank, you get these 3 predictions, and you get these 3 different distributions that are all supposed to be modeling the same thing, and they turn out to coincide. So everybody is happy. Okay, and since everybody's happy, I will end here. So.